Hello, everyone. I'm very sorry I couldn't be there in person for this conference. I was quite looking forward to it, but I've had to be in Australia this week. This is a recorded talk. I'm very honored to be invited to speak to honor Peter. So when I was a graduate student, I was deciding between studying harmonic analysis and analytic number theory. So I took Eli Stein's harmonic analysis course, and I took Peter Sarnak's analytic number theory course. I still vividly remember the first lecture of Peter that I went to. I think he started the class saying, you're all familiar, of course, with the representation theory of finite groups. We're now going to do the representation theory of SO2Z, or maybe SO2R. Now, I did not know the representation theory of finite groups at the time. And so I struggled a little bit with that class, and I eventually decided to study harmonic analysis with Eli Stein. But I did learn a lot from his classes, nevertheless. I still remember one little tip he gave early on that was very, very helpful for me. It was very simple. It said, if you want to estimate sine x, there are only two bounds you ever need to know. Right? One is x, and the other is 1. And that was the kind of level of math I could handle at the time. So that was very, very helpful. But I since talked to Sarnak after grad school quite a lot, and he was very, very supportive and helpful and kind. And I'm very thankful to Peter for everything he's done for me and for the rest of the math community. Okay, so I'll be talking actually mostly a survey about recent developments in a general cloud of problems, including childless conjecture, Peter Sarnak's conjecture, and what I call the Fourier Uniformity conjecture. Some of what I say will be joint work with Manomaki, Radzui, Shao, and Teravainen, and also Ziegler, actually. But I will actually not stress my own work so much, and this will mostly be a survey. So these conjectures concern many multiplicative functions or arithmetic functions, but we will focus in this talk for simplicity on the classical functions, the Mobius function, which you all know, the Lua function, which is the completely multiplicative analog of the Mobius function, so it is not restricted to square free numbers, the von Mangold function, which of course counts primes, and then the higher order divisor functions. So D2 is the classical divisor function, just counting the number of factors of number n. And then dk of n is the number of ways you can represent a number n as the product of k natural numbers. So these are, I consider them all to belong to the same family of functions. They're all related to each other. The easiest way to see the relation is to compute the Dirichlet series. And you will find that all these functions, the Dirichlet series, can be expressed in terms of the Riemann zeta function. And of course, Riemann zeta function is connected to the prime numbers. So all these functions see the prime numbers in one way or the other. From these formulas, you can imagine that there are various identities that relate one of these functions to the other. In particular, the von Mangold function, which is maybe the most interesting of these functions, can be written at some cost in terms of the other functions listed here. For example, you see here the Dirichlet series of the von Mangold function is the log derivative of zeta. And log you can try to expand as a Taylor series in terms of powers of zeta or zeta minus 1. And that will give you divisor functions. And so if you pursue that, you get what's called the Linux identity. So the Linux identity represents the von Mangold function as some alternating weighted sum of slightly modified divisor functions, what I call dk plus here, where I've just restricted the factors to be strictly bigger than 1, but essentially dk. So this is an identity relating von Mangold to dk. In practice, we don't use this identity too much because this sum is infinite, and we often lose control on the dk's as k goes infinite, as k goes to infinity. There's a substitute for this. There's a truncation of this Linux identity that is very useful. It's called the Heath-Brown identity. And it's a similar expression expressing the von Mangold function in terms of divisor functions, but now you can truncate the sum to any specified threshold k. The price you pay is that you need to then convolve each term by some truncated Mobius function. But roughly speaking, the upshot of this formula is that if you understand all the dks, or maybe the first 10 of them or so, then you also understand, at least in principle, the von Mangold function, although this extra convolution can cause some difficulty sometimes. Okay, So these functions all belong to the same family, but some are easier to understand than others. In this family, maybe the easiest function and the one that's most understood is D2, the second divisor function. So here, even just the classical Dirichlet hyperbola method can give very good estimates. And then, of course, we have more sophisticated techniques such as Glucksmann sum bounds and automatic form methods. And we basically understand almost everything we like to understand about D2. Decay, the higher decays are not as well understood, but they're at least still multiplicative. And also, their behavior is largely controlled by the small prime factors of a number. I mean, the large prime factors play some role, but the small prime factors, in some sense, dominate. And so, at least at the qualitative level, that helps because we understand small prime factors much better than large prime factors. The Mobius and Luber functions are less well understood. The way I think of it is they're influenced both by small primes and large primes. Just knowing the small primes that divide a number doesn't really tell you what's going on with mu and lambda. So you have the influence parity problem. You also need to understand large prime factors. On the other hand, they are bounded multiplicative functions, and so and on that level, at least, they are the nicest among all the functions here. And the most difficult function is the von Mangold function, also the one that we care the most about, especially if you care about questions involving prime numbers, because it's not multiplicative, it's not bounded, and it is completely determined by large prime factors. Small prime factors play no role at all. So it somehow is the worst of all worlds. What kind of questions do we care about? So I'll focus on three related questions. One is very classical, which is just controlling long averages. So if you take one of these functions, f in this family, say von Mangold or Mobius, you might be interested in the long partial sums. You just sum this function up to from n up to x. Or maybe you insert a weight g. For example, you might just be interested in a sum on an arithmetic progression, or you weight by some exponential phase or whatever. So these are long averages. Then there's short average versions, where instead of averaging all the way from 1 to x, you average from x to x plus h, where h is somewhat smaller than x. And typically, h would be x to a small power, or maybe log x. And you can also insert weights again. And you can either talk about fixed intervals, where you fix x. These are harder to control, or you get to average in x. Maybe little x varies in an interval from big X to 2 big X. And there we understand a bit more when we're allowed to average. That's sort of similar to controlling almost all short intervals rather than all short intervals. And then the hardest, but maybe the most interesting sums that we want to care about are correlations that really get to the microscale. So long averages give you the macroscopic scale distribution of your function. Short averages will tell you sort of mesoscopic information, and correlations really tell you microscopic information. So you take a small shift h, maybe 1 or 2, and you ask for correlations of f with a shift of f by h. That's a 2-point correlation. And more generally, you can talk about k-point correlations for different shifts. Okay, so let me review what's known about all these three questions, starting with long averages. So for the divisor function, we know quite a lot. So very classically, we can sum the divisor function, any divisor function dk up to n, and up to x. And just using even just the hyperbola method, you can get a main term, which is x times a certain explicit polynomial in log x. I think for D2, it's like 2 log x minus, log x minus 2, plus 2 gamma minus 1. Plus an error term, which has a power saving. It's x to 1 minus some constant. And people have tried to optimize this constant a fair bit. So for example, for D2, the hyperbola method gives you a 1/2 saving, and the current record is like 0.68. And then there are similar things for higher k. For von Mangold or Mobius or Liouville, we also have long-term control, but the bounds are worse. So this is basically the prime number theorem. So if you substitute in the best prime number theorem we have, which is the Vinogradov-Korobov prime number theorem, we can estimate, we can control the partial sums of mu or lambda or von Mangold, which we normalized by subtracting 1. And we save, so the trivial bound is x, but we save something somewhere between log x and a power saving. So some sort of quasi-polynomial gain here. We would like to do better, of course, but that's the Riemann hypothesis pretty much. Okay, in particular, RH is true if and only if we can improve these bounds to x to the 1/2 plus epsilon. Okay, and then finally, well, okay, so those are the sums without any weights. The next most complicated sums are weights restricted to arithmetic progressions. And you can adapt, you can do similar things, but now you need to also understand L functions. Um, these can always be computed. In the case of the divisor function, things get complicated because the answer changes depending on whether the residue class A mod Q is primitive or not primitive or partially primitive. So the way I like to think of these sums, the way to compute them is to actually try to find an approximate. So for each of these functions, you can find what I call a sieve approximate, F sharp, which is some tractable type 1 sum or major arc sum, if you wish, which is easier to work with. It's messier, but you can compute pretty much everything involving F sharp. And what you would like is a statement like this, that your original function and your F sharp, they have the same statistics on arithmetic progressions, that if you sum them on any arithmetic progression, you save an arbitrary power of logarithm over the trivial bound, so a Siegel-Wolfitz type bound. Gaining an arbitrary power of log x is the best we can hope for with current technology. If you assume there's no Siegel zeros, or if you assume GRH, or if you're working with decay, you can hope to do better. Okay, so what is the sieve approximate? So the simplest case is if you're working with the Mobius over Mangold function, then we have the Mobius pseudo-randomness principle, which based in this language tells us that the correct sieve approximate is 0, at least in the absence of Siegel zeros. For Mangold function, the Mangold function is mostly supported on primitive residue classes. So, a very simple approximate is what I call the Kramer-Granville sieve approximate, which corresponds to the famous Kramer-Granville random model of the primes. You basically take F sharp to be, you restrict n to the primitive residue classes modulo some reasonably large modulus W, which is defined here. And you have to normalize it so that it still has norm 1. And this turns out to be quite a good approximate to the von Mangold function, in that we do have the correct Siegel-Wolfitz theorem for F minus F sharp. At least if you don't have a Siegel zero. If you have a Siegel zero, you have to add some additional terms to get better accuracy. All right. Okay, for the divisor function, we do have good approximates, but they're not as easy to describe as for von Mangold, as for Liouville or Mobius or von Mangold. Again, because the distribution of the decays in arithmetic progressions is somewhat complicated. Although on the plus side, we don't, Siegel zeros are not relevant when studying decay. One relatively simple approximate was proposed by Andrew and Smith a couple of years ago. They observed that the divisor function, the kth divisor function is a divisor sum of the k minus first divisor function, just by definition, where you sum over all divisors m up to n. But you can truncate this. You can truncate m to be less than some intermediate threshold r. And then you need to renormalize the sum to be about the right size. But if you insert this renormalization factor, then this approximate dk sharp is a reasonably good approximation to decay. On any arithmetic regression, decay and dk sharp will have the same statistics to top order. Unfortunately, only to top order. The error only gains you 1 power of log over the trivial bound. This approximate is good if you only care about saving a little bit in the error terms. But if you want a really good approximate, you need to work with a more complicated formula. My co-authors and I did introduce such a formula. They do exist. Also, there was previous work, I think, of Duke and Friedland Ivanic. I mean, you can also use the delta method to create good approximates. But there's a more complicated divisor sum, where instead of dk minus 1, you have to insert some other polynomial in log n. But there is an explicit choice of dk sharp such that dk and dk sharp have excellent agreement on arithmetic progressions there, that their mean value, you get a power saving in the difference. This pkmr is quite complicated to write down. You can derive it heuristically by sort of using the hyperbola method and making some equidistribution hypotheses, just to give you a taste of how messy it is for D2, the simplest case. Then P is a linear polynomial. For m is less than r, it's just constant 2, and for m between r and r squared, it's a certain linear weight. So it's already moderately complicated here, and it just gets worse for higher k, but it is explicit. Okay, so So for every f in our family, there's an approximate f sharp for which we can control f minus f sharp in arithmetic progressions. Turns out that we can control f minus f sharp for other functions too. So for instance, if you can correlate f minus f sharp against exponential phases, e to the 2 pi I alpha n for any alpha, and you get Siegel-Wolfert type savings. This was famously done by Vinogradov for the von Mangold function, used, for example, to prove Vinogradov's theorem that every large odd number is the sum of 3 primes. And a similar argument also works for Mobius and von Mangold. It will also work for divisor function, although I think that's not, well, we have it in one of our papers, but I don't know the classical reference. This basically follows from the previous work. So if alpha is major arc, basically a rational low height, then this sum is basically a sum over arithmetic progressions, and you can use Siegel-Wolfert type estimates. If alpha is minor arc, then these G's have very good equidistribution properties, and you can start you use these combinatorial identities like Heath-Brown, like I mentioned before, and you can Cauchy-Schwarz away all this arithmetic stuff and just end up with some sums involving the function G, and you can get some cancellation in the minor arc case. Okay, so this was done for linear phases. The same method works for polynomial phases, like e to the alpha n squared. With a bit more work, Ben Green and I were able to generalize to even more complicated sequences, something called nil sequences, which I won't mention here. Possibly Tammy mentioned it in her talk earlier. But a typical example of the type of thing you can do is that you can correlate, say, the Liouville function with what's called a bracket quadratic phase. You pick two real numbers, alpha and beta, say root 2 and root 3, and you take e of the integer part of root alpha n times beta n. And that's some weird sort of what we call a bracket quadratic. It's almost like a quadratic phase, but more complicated. But we still can extract a Siegel-Wolfert type saving for this type of expression. And there are more complicated things of this type that we can do. Now, there's a very general conjecture in this area due to Peter. Tammy should have already talked about this in her talk, but I'll mention it again. Sarnak conjectured that the Liouville function, or also Mobius, in fact, is asymptotically disjoint from any deterministic sequence, defined as follows. You take any compact metric space, you take any homomorphism in this compact metric space, you assume this homomorphism is somehow rigid, it has zero entropy. So that's a technical term. It means that if you look at the orbits of length n inside this dynamical system, that there aren't too many of them. That if you approximate that up to metric errors of epsilon, the total number of such orbits actually doesn't grow exponentially and it grows sub-exponentially in it. So examples like circle rotations, null manifolds, certain skew shifts. But anyway, if you have a sort of a deterministic sequence, so not something like a Bernoulli system that can incorporate pretty much any arbitrary sequence here, but if you have a very deterministic sequence, very predictable sequence here, lambda is so unpredictable that lambda does not correlate with any deterministic sequence. So that's a conjecture. Thomas Ziegler would probably have talked a lot about this conjecture. So I'll just say that it's been verified for a lot of systems. So I mentioned, for example, the work that I did with Ben Green verifies it for no systems. Bourgain, Sarnak, and Ziegler verified for whole cycle flow, but it is open in general. We're also very interested in analogs of this conjecture for the prime number theorem for Mangold function, so prime number theorem on dynamical systems. This is, and not every deterministic system will have a prime number theorem. But there are some flows for which we do know. No systems again. I think skew shifts of analytic co-cycles is also known. That's work of Kanigaski and Matsui. It's expected for whole cycle flow, and there's some partial results in this direction, but I believe the conjecture is still not fully solved. Again, I refer everyone to Tammy's talk for this. Okay, so now we turn to correlations. So we fix some shifts, H1 to HK. I should have said these are distinct, and we look at K-point correlations. And as long as the shifts are distinct, the belief is that you can just approximate these Fs by their Siffer approximants. And so you should be able to approximate any correlation by the correlation of the Siffer approximates, which in practice are very easy to compute, or at least tractable. I mean, they're messy, but standard sieve theory methods can generally compute these things. So for example, if you're correlating the Liouville function, the Siffer approximate is 0, And so the Charler conjecture is that all k-point correlations of the Looper function are asymptotically trivial, better than the main term. You save a little o over the trivial bound of x. And the same thing should be true for the Mobius function. And then we have the Hardy-Looper prime tuples conjecture, which makes a similar conjecture for the von Neumann code function. But now this super approximate gives you a main term, the famous singular series, which is some arithmetic function of the h1 and hk. Okay, so these conjectures are largely open, unfortunately. And also you can do similar things for the divisor functions. Now the main term will be some explicit polynomial, which comes out of these super approximates, and you expect a power saving. Yeah, so what do we know about these correlations? So 1-point correlations are basically long sums, and we understand the 1 points. The 2-point correlations, we understand 2-point correlations if one of the factors is D2. So D2 has really good level distribution, and we have all these automorphic methods. We can understand correlations of D2 with decay, for instance, or decay with D2 with lambda, and there's lots and lots of estimates in this regard. But the moment you don't have a D2, we are stuck. For example, pair correlations of D3 are still not well understood. In some cases, if you make strong hypotheses, you can do better. So if you assume it's equals 0, then you can verify some cases of the Hardy-Littlewood and Charler conjectures. So in fact, the full Charler conjecture is known in the case of actually, you need an infinite number of Siegel zeros. I guess the conjecture is only known in ranges that are close to one of those Siegel zeros. And similarly, Heath Brown did something similar for 2-point Hardy-Littlewood. So you can get, for example, the twin prime conjecture, assuming infinitely many Siegel zeros. Also, if you, in certain function field models, we know some Charler and Heath Brown results, not all cases. Again, yeah, triple convolutions, triple correlations are still hard, even for D2, actually. But yeah, for certain function fields, there are also other tricks that you can do. But for general correlations, for example, Charler for, say, 2-point Charler, the only results that are known require some averaging. You either average the scale x, what's called logarithmic averaging, or you have to average in the shifts, h1 to hk. And there's a bunch of results, which I won't detail here. Okay, so there's a connection between correlations and long sums. So in particular, the Charler conjecture, which is basically saying that the Looper function at the microscopic scale behaves like random signs. That conjecture is closely related to the Sarnak conjecture. It says that at the macroscopic scale, lambda is unpredictable. It doesn't correlate with any deterministic sequence. So heuristically, you expect a connection. And there's some elementary arguments based basically on van der Kolk differencing and some moment calculations that if the Charler conjecture is true, it implies the Sarnak conjecture. So this was observed by Peter over 10 years ago, and there's now many proofs of this implication, combinatorial, probabilistic, ergodic, theoretic, and so forth. The converse implication is almost known to be true. It's true of an asterisk. If you average the Charler conjecture in X, so you do a Chazal average, which amounts to inserting a 1/n weight in the sum, and then the trivial bound is log x. Then we have the log average Charler, which says that you should gain something over the trivial bound of log x for this log average sum. This is weaker than the Charler conjecture. It's implied by the Charler conjecture, but not conversely. For instance, even k equals 1, just summing lambda of n over n, getting little o of log x is really trivial. That's half a page of elementary number theory. But getting the decay for the unaveraged, for the unlogarithmic average sum, that's the prime number theorem, right? Which of course is harder. But anyway, you can log average the Charler conjecture and you can log average the Sarnak conjecture, and they turn out to be equivalent. And the reason is because they're both equivalent to the log averaged Fourier uniformity conjecture, which I will talk about later. Okay, so the Sarnak conjecture we don't have a proof of yet, but the Charler conjecture, once you do this log averaging, we do have some progress. If we knew this conjecture for all k, we would get the log average Sarnak conjecture and also the log average Fourier uniformity conjecture, which I'll talk about later. So that would be fantastic. We don't have that yet, but we have some cases. So k equals 1 is elementary. as I just mentioned. K equals 2, I managed to do a few years back. And we also know odd k. Here there's a parity trick. Lambda is kind of has this has this odd behavior. If you multiply n by a prime, it flips the sign of lambda. You also flip the sign of any odd number of products of lambda. So there's a parity trick which lets you do the odd case. At first glance, that looks like we've solved at least 50% of the Charlotte conjecture, but that's a bit deceptive. The odd case is actually a lot less useful than the even case. The even case actually implies the odd case. There's a Cauchy-Schwarz argument, but not conversely. The k equals 2 case already has some useful applications. Yet knowing pair correlations of multiplicative functions lets you solve lots of other questions about multiplicative functions and even some non-multiplicative functions. In particular, I use it to solve something called the Ehrlich discrepancy problem, but I will not talk about that today. My original bound was very weak, so I managed to prove a slight gain over log x. I think if you unpack all of my arguments, it's like log x over log, a five-fold log x on the denominator. The number of logs on the denominator has steadily decreased over the years until we've gotten almost about as strong an estimate as you can hope for without GRH, which is that you can gain a small power of log x over the trivial bound. So that's a fantastic achievement, actually, of Cedric Palat, building upon earlier work of Helfgott and Matsui. But that's k equals 2, and the higher k, the bounds are still terrible. And for example, k equals 4, completely open. Okay, so these correlations, the main way we've made progress on correlations is to relate them to short averages, and I'll explain why later. But let me first discuss what is known about short averages. Okay, so you might want to control, say, the Womengo function or the Mobius function on some either a fixed interval of x to x plus h, or maybe you allow yourself to average over many intervals. If you want a fixed interval, then unfortunately we need the length of the interval to be somewhat large. For example, if h is large enough, we do have prime number theorems in short intervals, that the average of Mobius or Womengo or Liouville minus the mean value is little over the trivial bound. But this type of prime number theorem, until like 2 weeks ago, it was only known for h bigger than x to the 7/12. And this has been a famous barrier for quite a while to beat the 7/12. And it was just done very recently. And so you have just heard talks by Guth and Maynard, I believe, yesterday on this topic. But even if we assumed RH, and Guth and Maynard make some progress basically towards RH, even if we assume RH, these theorems are only known for down to x to 1/2. If you want weaker estimates, just like 0.99h or something, you can get something. You can enlarge the scale a little bit, 5.5 x to 0.525. I don't know if the Guth Maynard results improve this result, but still h has to be quite large. You can do better for the divisor function. For example, for D2, it's quite easy, even elementary, to get good bounds even on as intervals as short as x to 1/3. And you can shave that down a little bit to x to the 0.315. For D3, D4, and so forth, the bounds are not nearly as good, but there are some bounds. I didn't record the exponents here. Okay. If you average, then you get to do better. Okay, so for example, for Liouville function, if you want to control a single interval, you need 7/12, or a bit smaller than 7/12 now, thanks to Guth and Maynard. But if you allow yourself to average and you just ask for non-trivial bounds on the average, you can do a lot better. So if you want good bounds where you save a big power of log x, then you can use some zero density theorems. And until very recently, the best result was due to Huxley, and you could get down to x to the 1/6 for any of the functions I mentioned. But now that 1/6 has been improved very slightly by Guth and Maynard to some other fraction, which I didn't record here. And for decay, you even get a power saving in this case. But amazingly, if you're okay with just a qualitative, weaker saving, you can go below this. So there's this really important theorem of Manamaki and Matsui, which kind of pushes the multiplicative number theory, Dirichlet series methods to the limit. And you don't save a full power of log x, but you can save a power of log h, a small power of log h. But this works for any h that goes to infinity. So h can be as small as log x, which is amazing. but you can still get a gain here. So this is the Manamaki-Vadzuri theorem. So it's really the first theorem, I think, in this area that really gives some strong information of the microscale behavior of things like the Liouville function. And the same thing holds for the Mobius function. And in fact, for any bounded multiplicative function that's not pretentious, I won't talk about what pretentious means here. But basically not a Dirichlet character or something like entropy IT, or a Dirichlet character times entropy IT. Okay. If you replace the Liouville or Mobius function by the divisor function, we also have Manamaki-Vadzuri type theorems, but at a cost. We do gain a trivial bound. So here the mean value of decay is log k minus 1x. So you have to accept an extra log k minus 1 here. You can gain a little bit over the trivial bound, basically because of what I said before, is that the behavior of decay is largely driven by small prime factors. And you can still understand small prime factors here, as long as h is not too small. H has to be at least as big as a large power of log x. Below log x, there's some serious problem. The decay does fluctuate quite nastily below scale log x. But we don't quite get the optimal exponent here. But if h is much bigger than a log power, we do get some control here. We would love to have a similar result for the Riemann function. Unfortunately, that's only known on the Riemann hypothesis. Silberg controls, I think, the variance of such averages. Of course, for if you want fixed interval estimates at the scale rather than average estimates, we also have the Meyer theorem that says that this you don't actually have a prime number theorem at this scale. Okay, so the Manamaki-Vadzuri theorem, as I said, gives you microscopic information about lambda, and it was the key ingredient in proving this two-point Charlotte conjecture, log averaged two-point Charlotte conjecture. So at least in my proof, possibly Palat's proof doesn't need this input anymore, but my proof certainly did. Okay, so let me explain why there's a connection between these sort of short average estimates and these correlation estimates. So it's we're just exploiting multiplicativity at small primes. So every time you multiply a number n by a prime, the Liouville function flips in sign. So therefore, if you take a two-point correlation, lambda of n plus h, you can multiply both arguments by p for some prime p, and the product will still be the same because both factors flip by -1. So this suggests you can do a change of variables here. You can take this sum and replace n by pn. So pn, instead of going up to x, goes up to px, which looks like a quite different sum, but because we're doing log averaging, summing up to x and summing up to px is almost the same average if p is small compared to x. So we can substitute n by pn, but the price you pay is that we can only sum over numbers that are divisible by p. And also because of the denominator of n here, there's an extra p that shows up here. But the upshot is that the multiplicativity of the Liouville function allows us to rewrite this two-point correlation at shift h by a two-point correlation at shift hp with this annoying weight where you are restricting n to be divisible by p and then normalizing by p. Okay, so this is true for each prime p, so we can also average. So we average over all primes in some intermediate scale big P. Think of this as like log x or something. And so you can control this average, this correlation, by this average correlation times this annoying weight. So there is some trickery that lets us get rid of this weight. So on average, this weight is 1. Okay, so we would like to replace this this weight by 1. Now it's not close to 1 in variance. It's quite spiky. But there are tricks. Okay, so I managed to use a combinatorial argument based on information theory using Shannon entropy to show that for most scales p, you could actually replace this this weight by 1. In the specific case of two-point correlations, there's also expander graph methods. You can construct a graph where two numbers are connected if they if their difference is divisible by a small prime. And you can use that. Sorry, if the difference is a small prime, and you can study the expansion properties of that graph and use that to sort of remove this extra weight. But the upshot is that with some effort, you can remove this weight. And then the upshot is that you can control this two-point correlation by this average correlation. And this begins to look more like a small-scale average. So if this was averaging over not primes but natural numbers, this would basically be a short interval average. You're averaging over primes, but you can use the circle method. And essentially, you can write this average as combinations of terms that look like short-term averages. There's more terms here because there's several major arc contributions. This is the biggest major arc contribution. There's some additional major arc contributions coming from other major arc frequencies. But this average roughly looks like this, and this is the type of thing that you can control using the Mathematical-Radsby theorem. And the beauty is we don't need much to know about p. Any p that goes to infinity would suffice for this argument. Okay, so if you analyze this argument, you can actually the scales that you need the Mathematical-Radsby theorem to apply are slightly less than log x. So if you don't need to get down to log x or anything that small, something like log to the epsilon x would be enough. So if you controlled short averages on this scale, you would get two-point shallow. The expanding graph methods are specific to two-point correlations. For higher points, you would need to understand expanding hypergraphs, and we really don't have good good tools here. Hang on a second. Hello? Yeah, what's up? Yes, I am. Okay. Yeah, I'm at home. Okay. All right. Okay. Okay. All right. Okay. Wait. Shit. I have a dentist appointment. I've identified at 4:15. Okay. In about 4, I guess. Okay. Right. Sorry about that. Okay, so yeah, the hypergraph methods, we don't understand expanding hypergraphs, so we have to use this entering method, which restricts us to using scales up to log epsilon. If, for example, you wanted to control get the three-point Chowder, which we can do for the specific case by the parity trick, but if you wanted to get a more robust three-point correlation estimate that didn't rely on the specific properties of the Loover function, you would need to, if you apply the same method, you need to apply what's called you need to solve what's called the Fourier Uniformity conjecture. You need to generalize the Mathematical-Radsby theorem. So on almost all short intervals, you not only control the mean value of, say, the Loover function on this interval, but also the maximum Fourier correlation. So you correlate the Loover function with a Fourier phase, and crucially, you take the worst phase, you take the soup over all the frequencies, and then you average. It's important that the soup is inside the integral. And if you can do this for some h of size log to the epsilon, you can get three-point correlations. Using what's called higher order Fourier analysis, which I won't get into here, if you want to control four-point correlations, you need to control a similar statement, but where this linear phase becomes something like a quadratic phase. More precisely, something called a two-step null sequence, but I won't explain that in detail here. Okay, so this conjecture implies, like if we had this conjecture and the higher order versions, we would get all the log average Chowder conjectures and Sarnak conjectures, and it would be great. Okay, unfortunately, the Mathematical-Radsby argument that gives you the Mathematical-Radsby theorem, it relies very much on specific identities, in particular the possible identity. And it doesn't seem to apply to attack the Fourier uniformity conjecture. We've tried. Nevertheless, there are some other methods. So basically, by exploiting multiplicativity at small primes, we can actually show cases of the Fourier uniformity conjecture for reasonably small h. So as I said, if you can get down to h log x to the epsilon, we would have all kinds of applications. And we can't quite do that. We can get down to this intermediate scale of exponential of square root log x. This is a recent result of Miguel Walsh. And if you assume GRH, you can even get down to log to anything which is large. So log x raised to anything that goes to infinity. So log x is say the log x. Or if you like, log x to a fixed power c, but you get an estimate which goes to zero as you get a bound which goes to zero as c goes to infinity. So for Louveau and von Mangold, we have somehow just a small amount away from the Charlotte conjecture. We can also extend these results to some extent to the divisor function and the von Mangold function. For the divisor function, we get a similar. We can get x to the epsilon so far, and probably we can maybe push a little bit to something like the x plus square root of log x. And for the von Mangold function, unfortunately, for reasons having to do with relying on the Dirichlet hyperbola method, at some point we are stuck actually at x to 1/3. We cannot go below x to 1/3. There's also this previous barrier at x to 1/6, which Guthrie may not have improved, but there's a previous obstacle before that. Okay. But anyway, we are somehow really close. This is just this one sort of log barrier that we need to break in order to get the log Chalder and log Sarnak conjectures, assuming GRH. Okay, so in the last few minutes of the talk, I want to explain Walsh's argument. He calls it the contagion argument, which is giving us the best bounds currently on the local Fourier uniformity conjecture. Okay, so we are trying to understand a sum like this, local Fourier sums of the Louveau function, expecting those to be small. So we argue by contradiction. Suppose that this sum is not small, it is as big as the trivial bound. So what that means is that for a positive fraction of these positions, x, so for say 1% of all the intervals in this range, the Louveau function is correlating with some Fourier phase. So for each one of these intervals, there is some phase with some frequency alpha of x, such that lambda is correlating with, as a non-trivial correlation with E of alpha xn. So I'm going to write that rather informally as this correlation. I'm going to use the approximation symbol to indicate correlation. So alpha is somehow pretending to be like a linear phase up to a constant and only in some weakly correlated sense on various short intervals. Now, the thing that makes this hypothesis hard to use is that we don't initially understand how alpha depends on x. Okay, for every x, you have a frequency, but this alpha could be a completely arbitrary function of x. So the main step in all the progress on the conjecture is to first try to classify as much as possible what alpha of x does. What is alpha of x? So for example, we don't expect lambda to correlate with many different frequencies simultaneously. If you're already correlating with e to the alpha 1 times n, it's hard to also correlate with e to the alpha 2 times n if alpha 2 is very different from alpha 1. And we have a quantitative way of making that precise. It's called the large sieve inequality. So as a first approximation, every short interval should only come with basically one large Fourier, large frequency, significant frequency, up to the natural error given by the uncertainty principle. So we are averaging on an interval of scale h. So the natural uncertainty in frequency is 1 over h. You know, if you modify your frequency by 1 over h, or if you shift it by an integer. So if you modify by 1 over h mod 1, you don't really change this phase. This phase only changes by a constant, essentially. So you don't really change the correlation. But any change more significant than that should give you a completely different frequency. And so you should only have basically one frequency alpha of x per interval, and the frequency should be locally constant. If you move by distance h, the alpha should only vary by 1 over h on the average. Okay. So that's one thing we know. We understand that locally it is basically constant. What else do we know? Well, we know that lambda is multiplicative. Okay, if you multiply n by p, you basically just flip the sign. So up to a constant, you don't change anything. So at the location px, so maybe I will start drawing a picture here. Okay. So here's an interval x to x plus h. Okay, so you can multiply by p. You get a larger interval px plus ph. Okay, so if at this scale the Looper function is oscillating according to some frequency, then you can dilate by p, and because of this identity, you expect over here the Looper function should be sort of correlating like alpha of p, alpha x n over p. Okay, at least when n is a multiple of p, that the Looper function should sort of oscillate at this frequency. All right, so what? If you had two intervals, now suppose you had two intervals, x prime plus h, and another prime, p prime, such that when you dilate this interval by p prime, you get almost the same interval as what you started with. Then you get then the Looper function here would also oscillate at another frequency, alpha of x prime over p prime. And now there's a caveat, which is that the correlation with this function only holds on the multiples of p, and the correlation of this function holds only on the multiples of p prime, and those are sparse sets of this interval. But it turns out that as long as p is less than h, or less than h squared, maybe a square root of h for safety, these local averages on arithmetic progressions are usually very close to the global averages on the whole function. And there's an inequality of Elliott. It's a variant of the large sigma inequality that makes this precise. So as I said, we expect basically only one frequency to be present at any given interval. So we expect these frequencies to sort of be the same. You have to multiply out the denominators. And so the upshot of this analysis is we get a functional equation that whenever two intervals, x and x prime, are connected by these primes, then we get this functional equation. Now, this functional equation, if we didn't have this error and we did this mod 1, and we didn't have this restriction that p and p prime are prime, then there is an obvious solution to this equation, which is that alpha of t should behave inversely proportional to t. Okay, so if alpha of t behave like t over x for some constant t, then you can check that whenever px is equal to p prime of x, that implies that p divided by x prime is equal to p prime over x, and you would get this type of relation. So this type of inverse relationship where the frequency of your oscillation is inversely proportional to your location, that is consistent with the multiplicativity of the Looper function. So the whole strategy is to get a converse statement that in fact that this type of frequency, this type of behavior is essentially the only possible frequency correlation that you can have. That you would like to say that alpha must behave like t over x up to some errors. And actually, I'm cheating here. If you want to be really correct, you also have to add a major arc correction here. But let me not talk about that small technicality here. But basically, you want to show that the only frequency behavior that is permissible is behavior that looks like t over x. And then so then the space function behaves like e of t over x, which if you do a Taylor expansion, this is basically n to the it. It's a factor of 2 pi maybe that I'm suppressing. If you do the suitable Taylor expansion. So basically, the only frequency behavior that is dangerous is Archimedean characters, n to the it. And actually, if I want to be completely honest, I also have to twist this potentially by a Dirichlet character, but I'm going to ignore that aspect of the problem. And so if you believe that, then the only correlation that could possibly cause a problem is short interval correlations of the Looper function with n to the it. But it turns out that the mathematical residue theorem rules that out. And so this is why we have a hope of proving this conjecture. Okay, so let me clear everything. All right, so how do you get to this t over x? So this is Walsh's argument, and I think I will switch now to a whiteboard rather than show you the rest of the slides. So this is the contagion argument. Okay. So initially we have this interval x to 2x, and we pick some scale p, which has to be smaller than h. And this is the main reason why h has to be big, so that p can be somewhat big. And so we have lots of intervals for which we have lots of small intervals here, for which we have some frequency correlation. So for each of these intervals, we have some frequency that is that the Liouville function is correlating with. So what we do is that we start multiplying these guys by primes. So we take a prime p of size big P, and we dilate this interval to a slightly bigger interval of size now ph inside this bigger interval from px to 2px. And we find lots of connecting pairs. So we find that lots of these short intervals are connected to a single slightly larger interval up here. And so we get lots and lots of intervals, let's say xi, which are each of which dilate by some pi to a common interval here. And so we get many, many equations of this form. Okay, plus some error. Okay, so we have a system of equations, which in general is actually hard to solve if you try to solve it for all the x's at once. But if you locally just try to solve it for all the xj's that feed into a single big interval here, this goes interval I. It turns out that just by elementary number theory, you can solve this. It's basically a sort of a robust version of the Chinese remainder theorem, basically. And you can show that each of these alphas basically behave like some t, which depends on this interval over xi plus some small error. And actually, to be precise, there is, again, also this major arc correction, which I will ignore. But you can show sort of locally, the alphas do have this inverse behavior. But the constant proportionality depends on this interval here. But basically, what happens is that there is some other frequency parameter, t sub I, attached to this interval, which controls the behavior of all the intervals down here. So the structure, the Fourier structure of the Liouville function down here has somehow infected this larger interval. And so now this interval also exhibits some sort of structure. There's a contagion effect, that structure is contagious. Okay, and you can apply this argument all over the place. And so what you get is you get a large number of medium-sized intervals here for which you have a similar structural control on the Liouville function. And it turns out that you can run the same game again, and you can and these intervals will infect slightly larger intervals. So there'll be a larger interval p squared x to p squared x, and you get some control over here. Again, there's some correlation with something like a Fourier phase, and you keep doing this until you get to a really large scale. Now, the number of times that you can do this is kind of logarithmic. So things begin to break down if h is too small. But the idea is to stretch things to such an extent. So initially, these intervals are really tiny compared to x, they're of log size or x to the epsilon. But if you do enough of this contagion argument, you can eventually get some correlation at a scale which is quite large compared to the ambient interval, like something like maybe pkx to the 0.9. So you can turn a very small, short interval correlation into a much larger interval correlation, and then a lot of the previous theory starts working, and you can rule out this type of correlation, unless you look like one of these Endley ITs. So you just have to get big enough that you can use previous theory to get some sort of contradiction. Now, in order for this theory to work, it turns out, so there's this sort of natural graph that shows up, like you can connect 2 points if they sort of differ, if the ratio is given by a small prime. And you need these graphs to have kind of good expansion properties in order for this argument to work properly. And this is actually where the generalized Riemann hypothesis comes in. GRH helps you give you expansion properties. I mean, the eigenvectors of this graph are given by basically averages of p to the IT, which is precisely what the Riemann hypothesis lets you control. So with GRH, you get to have enough expansion that you actually get control on a really big portion of this interval eventually. You can make this t pretty much essentially constant on this interval. Unfortunately, this type of expansion probably only happens if you use primes that are bigger than log x. For primes that are less than log x, there was no expansion because of the Chinese remainder theorem, the product of all the primes up to log x is much smaller than x. And so just using multiplicativity as small primes, you cannot explore the entire macroscopic space just using this multiplicativity. And so if you want to break the barrier, the log x barrier, and really get good control at small scales, you need to somehow not just use multiplicativity at small primes, but somehow use also multiplicativity at large primes, even though initially your intervals are shorter than the primes you want to use. So this is the stumbling block. The Matamaki-Razuri argument did somehow get around this through the magic of Dirichlet series identities. They were able to somehow convert short average questions to long average questions in a way that they could suddenly use multiplicativity at primes that they couldn't use before. And we've been trying to make that work for uniformity conjecture, so far without success. But I feel like we're just one breakthrough away from getting both the Childer conjecture and the Sarnak conjecture, at least with log averaging. So thank you very much. And again, I'm very sorry that I can't be there in person.